So a colloid or a colloidal dispersion is different than a solution. It's a mixture where you have the dispersed substance is finely divided. These colloidal particles are small enough that they can stay suspended in the liquid, but they're larger than regular solute molecules. They're typically in the range of 1 nanometer to 100 or 1,000 nanometers in diameter. That's significantly larger than most molecules. So with colloids, what we'll typically see is more of a cloudy appearance. These particles now are large enough that they can deflect light. I'm going to skip this for a minute. I'm going to talk about the Tyndall Effect. So this is the Tyndall Effect. This happens with colloidal dispersions. You shine a light through a colloidal solution or dispersion, and you can see where the beam of light is going through. When you shine light through a solution, you can't see where the beam of light is. The reason you can see it here is because those particles are large enough to reflect the light. In a solution, the particles are too small. So it's similar to what happens when the sunshine is streaming in through the window and you can see sunbeams. What that means is you have dust in the air, because that's what makes it visible. If the air is really clean, no dust, then you're not going to be able to see the sunbeams. So that's one of the important differences between a solution and a colloid. And you can use that and you just shine a light on it and see if it's a colloid or a solution. So let's go back here. If you look at the particles in a colloid under a microscope, they have a distinctive jittery motion that's called Brownian motion. I've got a video of this. We're in chemistry, we don't use microscopes. The jitteriness here is caused by collisions of the molecules, of the particles with molecules in the liquid. So this is looking at pollen grains in water. So that's the Brownian motion. They almost look like they're alive. That was it? I know, right? But, if a picture's worth 1,000 words, what's a video worth? So, of course, there's a backstory to that. Brownian motion was discovered by a guy whose last name was Brown. And initially he thought those particles were alive because they sure look alive. Like they're moving, right? How do inanimate things just move like that? They eventually realized that what was happening is the water molecules that you can't see are moving around, right? Because they have kinetic energy. And they are bumping these larger particles that can be seen under a microscope. And so all of that jittering is from water molecules hitting it. It's a little bit like these are beach balls in a big crowd, maybe a graduation or a football game or something. And people are hitting the beach balls, and they're just kind of going crazy, all different directions, right? So the water molecules would be like the people, and these larger particles would be like the beach ball. It gets bounced around. If you add enough soap to water, the soap will form micelles, and the micelles are large enough to scatter light. So I talked about this a little bit in a previous lecture talking about how soap works. So here we have an example of a soap molecule. You've got a polar head, it's ionic, and then you have a nonpolar tail. And so these nonpolar tails do not like the water, and the water doesn't like them either. And so the soap tends to form these micelles with the polar heads around the outside of the sphere and the nonpolar tails in the middle. And it's kept stable because there are electrostatic repulsions between the micelles. So there are sodium atoms out here, but this has a negative charge, and so this particle and the two micelles are going to repel each other. So they'll form these micelles and it'll be stable, but it is a colloid because it scatters light. And this works to get rid of grease because the grease and oils can dissolve inside of the little micelles, and then they're able to wash away. Macromolecules are large molecules, such as proteins. Those also form colloids. So if you look at milk, right, you can't see through the milk. It's actually a colloidal dispersion. It's been homogenized so that it doesn't separate into the fat creamy layer on top and the skim milk on the bottom. But you can't see through it because those particles are larger, they're proteins. Here's some examples of different types of colloidal dispersions. There's actually a lot of them that we encounter. Fog, we saw some of that this morning. Water droplets in air. Those water droplets are large enough that they scatter light, right? That's why it's hard to see when we're driving. Just normal humidity, those particles are smaller and it's not a problem with visibility. But in the fog, you've got a colloidal dispersion. So there you have a liquid being dispersed in a gas. You can have solid aerosols. We've experienced this recently too from the fires. Smoke. This is small particles of ash in the air, and that causes a hazy appearance. We've got a solid dispersed in a gas. Foam, like whipped cream, which you may have experienced this week at Thanksgiving if you had pie. That's a gas dispersed in a liquid. So the gas is air bubbles dispersed in butterfat. Emulsions, such as milk, are also a type of colloidal dispersions. You've got fat globules and proteins dispersed in the water. You can also have solid emulsions. Some precious stones, like an opal, is actually water dispersed in silica glass, and that's what gives it its really cool appearance. And that is the end.